Okay, so firstly, any questions? I sent around a design homework last night and also solutions to the first homework. We have graded the first lab. Basically, everyone got full score, so not very interesting. That was an easy lab. The first homework, the department just assigned a reader, so she will be grading this week. So hopefully, maybe end of this week or by Monday or so, we'll hand it out. Um, so, any questions? Anyone looked at the design homework? No. Okay. It's going to take a bit of time. The spec is pretty foreboding, 4 pages, so there are a lot of sort of nuances, and you have to do it following kind of details we have there, particularly how you name the terminals, where you locate them, because without them we will not be able to kind of run our script. So in the first homework, if you didn't stick with the format, we still give you most of the points. I think 80% or something like that. But this time around, it's too complex for us to manually grade. So if you don't follow the specs, it will basically reduce to 0 grade in that case. So very important. Carefully read through it. If you have any ambiguity, post on Piazza or answer it, or just come and meet me. We'll also, so this is due on Friday. We'll also be handing out the second problem set based upon the material we're covering, and that will be due on Monday. Next week, we have the midterm on Wednesday. So my plan is, so basically all the material covered through this week is going to be in the midterm. Monday, I'll spend some time as a review, and then for the extra office hours, longer office hours, on Tuesday, so that you can come by if you have any questions and all. Now, for the Monday session, if there are topics that you would like me to go through, or any problem that you would like me to work out, then write to me, and I'll kind of select. If you don't, then of course I'll have to just make my best assessment out there. So write to me as you're solving stuff in the book. If there's something that doesn't that you're unable to, so that's your opportunity. Finally, I was counting how many people submitted the problem set 1, and there are 3 students who didn't submit in the class of 79. I would say that homework is the easier part of getting the score, so students tend to do somewhat worse at the exams with the time pressure and all. So if you are not doing the homework, you are actually kind of letting go of easy points, so try not to submit. Anyway, questions? No? Okay. Now, there's one request that I should go through the how to make big encoders or the smaller encoders again. So I'm going to spend some time doing that, and then move on to other topics. So encoder is the reverse of decoder, and it's a logic module which takes a one-hot signal and then binary encodes it. So that's its basic functionality. And so in effect, if I take an n-bit input to an encoder, and then I'll map it into a binary coded one. So for example, a 4-bit to 2 bits. There are 4 possible options, and the binary encoding would therefore take 2 bits of it. So this is the truth table of 4 to 2 encoder. It has 4 inputs, it has 2 outputs, and not all the 16 possible 4 input combinations are valid out here, because one hot coding means that one and only one bit is a 1, rest are 0. So if I give you an n-bit input, there are only n possibilities, and the remaining 2 to the power n minus n are invalid inputs. They are not proper one-hot coding. So in an example like this, then if nothing else is specified, then you could say they don't care. That's one possibility, or as last time we also discussed, possible other options include to go to a safe value like 0, 0. So there are all kind of possibilities. Now, if you take it as a don't care and you work out this example, it's actually a pretty simple truth table. So both B0 and B1 are basically just OR gates each. So it's a pretty simple 4 combinational logic. and that's what it looks like. Okay. Okay. Now let's say we want to design a larger encoder. Now, one way we could do it is certainly create a larger truth table and work off that. But as we saw in the decoder, as we saw in the decoder, if you do this kind of building bigger decoders from smaller decoders, we had fewer gates being used at the cost of higher delay. So one would guess encoder also might be worthwhile to do it that way. So smaller encoders and leading to bigger encoders from that. Now to do that, unlike decoders where we could just use the smaller decoder as it was, in encoder you need a little bit of additional help, and the reason has to do with this problem that given a 4-input encoder, not all possible 4-bit values are valid values. So what happens is, so intuitively, if I give you 4:2 encoders, then I have a 16-bit input in this case. Then first thing you're going to start with, let's chop it up into groups of 4. So we did that. We have 4 groups of 4 out here. The problem is that in that 16-bit, only 1 bit is 1. The rest are all 0. So let's say we decide that A11 was 1, let's say. So that means A12:15 is all 0. A4-7 is all 0. A03 all 0. So the bottom 2 encoder and the top encoder are not seeing valid one-hot coded input at all. So you have to kind of take care of that somehow. So what we do is, besides the regular binary encoded output that an encoder has, which is the blue color, we are also going to have an additional output, which is basically going to indicate is it a valid one-hot coded? Is this encoder seeing a valid one-hot coded input or not? So if an encoder is seeing a valid one-hot coded input, then the red output will be 1. Otherwise, it would be 0. Now, in our particular case, 3 of the 4 encoders are going to see all zeros, and 1 encoder would see one of the 4 inputs being 1, the rest remaining 3 being 0. So we introduced this red one, whose job is to that it would be 1 if the input is valid one-hot coded. So this one is 1 if and only if input is one-hot. Okay, and the blue behaves. Blue would behave the way it normally would, except that we place the additional constraint. We basically also say that if an encoder is not seeing a valid input, then the blue output should be 0, 0. So instead of being something arbitrary, if the input to a encoder is not one-hot coded, then the blue output should be 0, 0. So that's the additional constraint we place. So we basically say that the blue color is 0, 0 if not one-hot. So we made these 2 changes to our encoder. We introduced an extra output, and we made sure that the 2-bit output is 0, 0 if the input is not valid. Now what happens is the following. We feed the red outputs. We feed the red outputs to another 4:2 encoder. So one of the red output would be high. The remaining would be all 0. So the one which will be high will correspond to which group of 4 bits is the bit residing in. So if you think about it, if I take these 16 inputs and think of 4 groups of 4, then the group number designates the upper 2 bits of my final output. So I have 16 input, I'm going to encode it into 4-bit. Which group number I am? If it is in group corresponding to 0 to 3, then in the binary encoded version, the upper 2 bits would be 0, 0. If it is, if the one-hot input is in 4 to 7, then the upper 2 bits are, in the binary coded version, the upper 2 bits are going to be 0, 1, and then 1, 1, and finally sorry, 0, 0, 0, 1, 1, 0, 1, 1. So we feed it into another encoder, which would do exactly that. So in our case, if A11 was high, then the upper red and the bottom two reds are 0, and the red line which is coming from the second from the top encoder, that's going to be 1. So so this encoder is going to see 0, 1, 0, 0, and therefore it will spit out 1, 0 on its binary encoded output. That's a standard 4:2 encoder. So we get the upper 2 bits this way. The lower 2 bits, we are already getting them. The only problem is that which we don't know beforehand which one of these 4 are giving us the correct lower 2 bits. So A11 is is the highest bit of this group of 4. So this guy is going to output 1, 1. This 4:2 encoder. The rest are going to output 0, 0. So what we now do is, and this is kind of this bit of a weird notation, but when you see this kind of thing where I have an OR gate and its output is 2-bit and each one of its inputs are 2 bits, what it is really referring to is I have 2 OR gates. One of them is operating on bit number 0 of each one of the input and produces bit number 0 of the output. The second one is operating on bit number 1 of each one of the 4 input and is going to be outputting bit 1 of on the output. So it's really 2 OR gates next to each other, but this style of drawing is used in Logisim also to save clutter, because otherwise I have to draw 2 OR gates and then kind of use bus splitters to feed lower bits to one of the OR gates and upper bits to the other OR gate. So this kind of simplifies notation. So this really is 2 OR gates out here. So now in our example, what will happen is, so let's say A11 is 1. So we are going to see a 0 here, we are going to see a 1 here, we are going to see a 0 here, we are going to see a 0 here, and then we are going to see 0, 0 on this upper blue line, we are going to see 1, 1 on the second blue line, we are going to see 0, 0 on the line coming from here, and finally we are going to see 0, 0 out here. So what this guy is going to produce is seeing 1 on input, the third input from top, so it's going to output 1, 0. And this guy is seeing 0, 0 on the top and the bottom 2 lines, and in the middle one it is seeing 1, 1. So the lower OR gate is going to see a 1, and the upper OR gate is also seeing a 1. So these 2 OR gates are going to output 1, 1. And therefore my total thing, this and this together, is going to lead to 1, 0, 1, 1, which is what we want. That's 11. Okay. Okay, so what is really happening is, let me do the following. I have an OR gate where each one of the input is 2-bit. What this really is equivalent to is 2 OR gates, each one of them having 4 input. And this one gets the bit 0, and this one gets the bit 1. So for each one of these wires, bit 0 goes to this OR gate, and bit 1 goes to the upper OR gate. So now in our example, we had 0, 0 here, we had 1, 1 here, we had 0, 0 here, and we had 0, 0 out here. So now what this guy will see is it will see a 0 here, 1 here, 0 here, 0 here, so output is 1. And this guy, by the way, incidentally is seeing the same thing, 0, 1, 0, 0, and so it too gets a 1. So the output is now 1, 1. So it's two OR gates, but we draw them as if it's a single OR gate, but each input has now n bits. Okay. Any other question on this? Okay. So this approach you can use for other type of encoder things also. So for example, so in this case we were doing 16 to 4. If we were doing 32 to 5 bits, and I had these 4 to 2 encoders, so now I'm going to have 5 4 to 2 encoders, and then I'm going to be combining them. So I'll go through examples for more complicated ones a bit later. But the idea is the first stage of encoder is basically giving you two pieces of information. It's firstly telling you what the lower 2 bits are, that is the blue line, and then the red line is telling you which one of the groups. So in our 32-bit example, it will tell us which one of the 5 groups it is. Now the problem we have is we don't have a 5:2 encoder in that, we don't have a 5 to 3 encoder, so you'll have to again kind of make it up using simpler encoders. I'll let you ponder about it a bit more, but usually you are going to be given powers of 2, so you're going to work off that. Going back out here, if let's say, for example, I had given you if I had given you, let's say, yeah, so we have 16 out here. So let's say I've given you 32. So now what will happen is that the first stage, since I have 32 inputs, first stage is going to have another 4 of these encoders up there. The lower 2 bits, each one of them is giving me the lower 2 bits. And then I will have 8 red lines. And those 8 red lines are encapsulating which one of the 8 possible groups of 4 I am in. And that you will have to reduce down to a 3-bit number. And what you'll do is you're going to repeat the same process. I have 8 lines, so I'm going to feed them into 2 4 to 2 encoders, which will now give me the lower 2 bits of the upper 3 bits. And then finally, I'll figure out which one of the 1 bit it would be. So I'm going to do that example later on, but you basically kind of cluster things in groups of 2 is going to be a strategy. And I'll have the TAs also kind of go over a few of these examples. But the main point to remember is we create this special encoder where we have this kind of additional output which says, hey, I saw a 1 on the input. And in your first stage, one and only one encoder is going to see see a valid 1 hot code, and the rest are going to see all zeros. So moving away from encoder for now, another module which is very useful is multiplexer. So multiplexer is, as kind of name implies, we kind of use it in, it's kind of like mixing bunch of things, and then you are going to be selecting one of them. So there are many things coming in, but only one thing going out. You're going to select which one to go out. That's kind of the intuitive idea. So oftentimes it happens, I may be getting data from multiple sources, but I need to take data from one of them. So I may have sort of 4 possible sensors, but my CPU might process only one source. So I will need some sort of a device, kind of like a switch, which I could say, take data from input number I. And whatever is the data on input number I, pass it through to the output. That's the functionality we want. So what in general we have is, we will have n inputs. Each of them may be k bits each, some k, so let's say 8-bit number or something. Then additionally, I will have another input which will tell me which input is of interest to me. So for example, let's say in my example, I have 4 sensors, and I want to pass through the data for one of them to the CPU for processing. So now I need to tell my multiplexer which one of those 4 sensors to pick. Now, one way I could do it, I can use a 2-bit input and then encode it. 0, 0 would mean sensor number 0, 1, 1 will mean sensor number 3, and so on and so forth. Alternatively, I could use a 1-hot code. So if I have 4 sensors, I will take 4 bit of control, and it would be 1-hot coded. If bit number 0 is high and the remaining 3 are 0, that would mean sensor number 0. If bit number 1 is high and the others are 0, sensor number 1, and so forth. So in this slide, what we have is we are going to use the 1-hot code. So what we see out here is a multiplexer. It has n inputs, input number 0 through input number n minus 1. Each one of them is k bit. So I have n sensors. Each one of them is outputting a k bit number. This is my mux, and I'm going to tell the mux that select one of the sensors, select sensor number I. And then whatever is the data appearing on that input, so let's say I tell it, take sensor number 3. So A3, the k bits of A3 will pass through to B. The rest are suppressed. And this input S is the selection input. So this is called select. It's basically saying which input to select. And what we decided to do out here is, since I have n options, because I have n possible inputs, we are going to use an n-bit 1-hot code out here. So logic-wise, it basically becomes like the following. Select one of the n k-bit input, using the value on S to tell me which one to select. So it basically says that if S of I is 1, that means I want to select input number I. So I say B is equal to AI, and B is k-bit, AI is k-bit, and SI is 1 bit. And if SI is high, then all the other S0 through I minus 1 and I plus 1 through N are going to be 0 because it's 1-hot coded. So I let S tell me what is I, and then I use that input to pass through its value to B. So literally, it's like a switch. It's an n-way switch. I'm telling what's the setting of the switches. S is a select. It's telling where to set the switch. In our example, the switch is set to input number I, and whatever appears on input number I passes through to the output. And nothing else. Others are kind of suppressed. We see this kind of stuff in many devices. Like if you look at your, let's say, home stereo system, they typically have a source select, where they let you select, get the data from whatever DVD player or your satellite box or something else. So basically, it's selecting the source. It's exactly the same thing happening out here. We are selecting which one of these sources are feeding to the output. In our case, sources and the output are all some k bit each, and we literally take all those k bits and move them to the output, and we keep doing it all the time. Anyone can think of other examples where you see this multiplexer type functionality in kind of devices that you play with? Where kind of you let it select which one to pick. So nowhere else, you don't see this functionality anywhere? Come on, guys. Go ahead. Huh? Oh, like where do you see multiplexer in like devices? Where I have to select a source and have X value go into the output. Routers. Yeah. Network routers. They have many ports, or your Ethernet switch, many things connected to it, and they kind of go out. Now, internally, what's happening there is that you kind of have to, happening is there's another processor sitting there which very rapidly decides which one to pass through. Okay, and it kind of keeps taking that. Patch cord systems are kind of like that, except they're literally wire them together. There are other places like, let's think for example, many devices have two-way switches which have three settings, an off setting and then two on settings, like you can get something from one place or another. Like your swimming pool system might have this kind of controls, very common. Oftentimes, other type of control security systems and all that form. Your TVs have this source functionality built in, right? I mean, again, they typically provide a source. So this multiplexing thing is very common, commonly present. That I have to select from one of the source and then use that for further processing. So multiplexers are what provide that. And one way of thinking of them is, again, there's a switch, and S is telling where the switch is connected. Is the switch connected to A0 or A1 or AN-1, and S is controlling that. So if S of I is high, then the ith input is where the switch is going to be. Okay, so how will we implement something like this? So one way, of course, we could do it with a switch, but we want to do it with a gate. So like in a mechanical system, you can imagine a rotary switch with n possible settings, and somehow I kind of have the switch move to the right setting. But we want to do it something like this with gate. So let's say we want to create a 4:1 multiplexer. I have 4 sources, and I want to select which source gets connected to the output. And for now, imagine that k equal to 1. That is, I have only 1 bit data coming in from each another source, and I need to feed it to the output. So this logic does that. So if you think about it, S is one hot coded. So S0, S1, S2, S3, exactly one of them will have a 1 value. Everything else would have a 0 value. So let's say S1 is high. If S1 is high, then the second gate out here is going to be enabled. So whereas other S0, S2, and S3, since they are 0, so the output of the bottom 2 and the top AND gate is going to be 0. Now, what about this gate where S1 is high? What would its output be? If S1 is high, then what's the output of the AND gate? A1, exactly. So because we have A1 and S1 is high, so the output is A1. So the AND gate is going to pass through A1. Now this OR gate is going to be seeing, so let's kind of write it down. So we are using an example where S0 is 0, S1 is high, S2 is 0, S3 is 0. So that means this is 0, this is 0, as was just pointed out, this is going to be A1, and this is going to be 0. Now look at this OR gate, what will happen now? So I have 0, or A1, or 0, or 0. What would the output be? Anyone? A1, right? When you OR something with 0, you get the, so in that case, B becomes A1, and that's exactly what we wanted. With a different setting of S's, something different will sort of pop up. And now let's say I want to create a 4-bit multiplexer. That is, I have 4 inputs, but each input is 4-bit. What would you do? Yeah, you just use 4 of these, right? They will have a common control, but of course the A bit will differ. So I'll just use 4 copies of these, feed bit number zeros, bit zeros of all the 4 A's into one copy, bit 1 to another copy, bit 2 to another copy, bit 3 to the third copy. The S would feed the common to them. So the same S0 will feed to all the 4 copies, same S1 will feed to all the 4 copies. So I can make an arbitrary large multiplexer. If you look at your like CPUs, like nowadays microprocessors are 32-bit or 64-bit. They use these kind of multiplexer aplenty. So you will have a 32-bit multiplexer or a 64-bit multiplexer, and then like in a microprocessor, it could be that the data could come from external memory or a local cache or some registers in the CPU. So many possible sources, and so multiplexers are very, very commonly used inside the CPU, very large multiplexers. And this one sort of achieves that. Now, let's imagine that S, instead of being one hot coded, was given to you in a binary coded format. So in our case, we have 4 options. I could give you a select which is binary coded, which is 2 bits. But now I want to make a multiplexer. How can you do it? So I want to make a multiplexer where the 4 inputs, A0 through A3, but now I have a binary coded select. Okay, let's call it X. And now it is 2-bit because 2 bits give me 4 options. Using the modules we have studied thus far, could you make a multiplexer?
You will put a decoder in front, and then decode it.
Exactly. So you take a 2 to 4 decoder. A 2 to 4 decoder's job is to take binary coded input, produce 1 hot coded output. So you use that and then use this multiplexer, and you're done. So one thing I would like you to start kind of getting into the stage is that these modules often kind of mix and match, and you can create other variants by kind of combining them together. So we saw decoder, we saw encoder. You can use them as a primitive together with this one hot coded type multiplexer to create a different kind of multiplexer where the control input, the select input, is now locked to n bits as opposed to n bits. And this is something very common in engineering. You don't kind of do things from scratch. You make use of these libraries of modules. Logisim, if you look in the left panel, has a whole bunch of them. Now, sometimes when I give you a problem, I will say you are limited to using something, only certain subsets. So like in the design homework I handed out yesterday, you are only allowed to use NAND gates and inverters. Okay. The problem would be trivial if I were to let you use all the modules available in Logisim. So I wanted to make it harder for you, I guess. But generally, kind of the idea is that these modules you can use. And the only reason not to use is that they usually come with a efficiency cost relative to kind of doing everything from scratch. But then there is efficiency of design and then the efficiency of the designing. Reusing modules improves design efficiency, makes you efficient, but maybe your design may not be as good. So anyway, this is a multiplexer. Now, this kind of multiplexers are very, very commonly used. Like I said, in CPUs and all, they are large multiplexers. So people try to implement them more efficiently. And doing it with this gate approach oftentimes turns out to be very costly. Imagine if I had a 64-bit multiplexer, 4:1, 4 input to 1 output. I would need 64 times 4 AND gates, and I will need 64 OR gates. Each one of these, like a 2-input AND gate, is 4 plus 2, 6 transistors in our technology. So number of transistors kind of add up. So people always like, could we do it more efficiently? And it turns out there is a way to do it with kind of a different style of implementing things than using our NAND gates and OR gates and all. So I'm going to briefly talk about that. And this is something that gets used quite a bit. And this is something called tri-state gates. So it's a funky type of gate. What it does is the following. So let's look at the right one. So the symbol is this. It's triangle. It has an input. It has an output. But it also has a control line. It's called enable. So I have an input A. I have an enable signal. And I have X. And what happens now is, this is like a switch. If E is high, then X is equal to A. But if E is low, then X is disconnected from A. As in, it's a floating piece of wire. It's not being driven by any voltage. So what happens then is we need some special symbol to denote it. When it is floating, it's neither 0 nor 1. No one is driving it. So we represent it as, we are just going to call it disconnected for now. So what you are seeing out here is if E is 1, then X is equal to A. So E1, A0, X is 0. E1, A1, X is 1. If E is 0, then irrespective of whatever is A, output is just disconnected. It's just a floating piece of wire. So those of you who are electrical engineers, many of you are, if I have a floating piece of wire, what is its impedance to the ground? Resistance to the ground. Anyone? Huh? Infinity. Very high. Right? It's basically going through the air. So it's not infinity, it's going to be some gazillion mega giga ohms, but it's very high. So it's called high impedance. So this disconnected state is usually referred to as high impedance, or is written as high Z. Z is the symbol electrical engineers like to use for impedance, so it's high Z, or high impedance. Now again, if I have a floating piece of wire, going back to your physics courses, relative to the ground, so it has a very high resistance, what else does it have? The current is 0, but like, think of like you have steady resistance, capacitance, inductance in your basic circuit classes, hopefully, or at least in physics you would have steady capacitance. So a wire over earth, ground, which is conducting, it forms a capacitor. So wires have capacitance to the ground, right? Those capacitances, in a chip, and the wire is going to be sitting above a piece of silicon, so the capacitance is going to be between silicon and that wire. And therefore, that capacitance can store some charge. So when you have a floating wire, at the point it became floating, it may have some charge on it. And it will hold that charge for a while until capacitors leak, so that charge goes away. So if I put a charge on a wire on a chip, so like for example, let's say E was high and A was 1. Then according to this, X will become 1. And now let's say I make E to 0. So now suddenly the wire at X is disconnected, but it still has a capacitance which holds the charge. So it actually will keep its value of 1 for some time until kind of it leaks away. Okay, that is electrically what is going to happen. But what what it would mean is this capacitance is going to be, voltage is going to be decaying. It will be very susceptible to noise. If there is some big electrical spike nearby and all, that capacitance will get disturbed. So it's a complicated electrical phenomenon which will kind of accompany it. But the nice thing, and we'll see how we'll make use of it, is that it is disconnected. This guy on the left is exactly like this, except that we have a bubble out here which indicates inverter. So what it means is if E is high, then output X is the invert or complement of A. So that you see out here. If E is high, A is 0, output is 1. If A is 1, E is 1, output is 0. And if E is 0, you have disconnected. So the right-hand circuit is called tri-state buffer, and the left circuit is called tri-state inverter. And they're called tri-state because the output can have 3 possible states: high or driven 0, and high Z or disconnected, or a bunch of other names given to that. So now what's happening is what we really have is a switch which we are controlling, and the switch could be inverting or not, but when it is connected, the input drives the output. When it is disconnecting, the output is disconnected. And we see these kind of switches in many devices. Our electrical switches are like that. What other device do you see in your electrical stuff at home which act like this, where there's a control input and the switch is controlled based upon the status of that control input? Huh? Say it louder. relay. Relay. Yeah, relays. Anyone knows what a relay does? How do they work?
We'll just see the inputs high and
Yeah, and you know, under the hood, how do relay? I mean, you find relays in many devices, and like, yeah, go ahead. Let's see. It's a solenoid switch, exactly. So it has an electromagnet inside it. When you apply so relays come in many varieties. So let's say if there is a relay which is normally on. So the switch is normally connected. You charge the control thing, then the electromagnet basically literally moves the metal arm and disconnects the switch. And they come in the reverse direction as well. You find them in wherever you are switching high current. So you will find them in like control panels for swimming pool. You'll find them in control panels for HVAC equipment and things like that. So they are basically like these, except that they are carrying large amount of current. You can also, so they come in kind of little packages. They sort of literally do put them on boards and all. So there are those solenoid magnetic type. There are also semiconductor relays. They are made using some special technology so that the transistors can carry large amount of current. But conceptually, they all are like this. They are a switch, they disconnect. Another place where relays were used very heavily were in the old telephone system. The old telephone system, the big telephone exchanges, were nothing but like gigantic collections of relays. And like you basically connected one telephone line to another like that. Okay, so why does all of this matter to us? In our case, it turns out that we can actually make multiplexers very easily with this. So this is how it works. Let's look at this circuit. So what we have out here is a bunch of tri-state inverters.
high impedance, high capacitance. The high impedance and capacitance are seen from the output to the ground.
Output to the ground. Yeah. So it's high impedance or high Z or a bunch of Okay, so let's look at this circuit. So now what we have is, I have four inverting tri-state inverters connected this way. I have E0, E1, E2, E3 as the four control inputs. I have four inputs, A0, A1, A2, A3, and I have an X out here tying them together. Now let's say E's were one hot coded. So we make sure that only one of them is high and the remaining are low. So now what would happen? Let's look at, actually let's try out what would happen for the first row. All the E's are 0. So what do you think will be the state of X? So if E is 0, what happens to the four tri-state inverters? They're all disconnected. So what would the state of X be? IG. It would be disconnected too, right? I mean, it's not being connected to any one of them. So in the first case, we are going to have high Z. What about the next one? Inputs are 0, 0, 0, 0. Actually, I think my tables are wrong, so let's call this thing E0, E1, E2, E3. So if that's the case, then what would happen to the output? So I have 0, 0, 0, 1. So switch number 0 is, this guy is disconnected. 1 is disconnected, 2 is disconnected, but third is on. It feeds A3 to X. So X is going to be A3 prime because it's inverted. So if all the switches are off, output is IV. If one of the switches on, then the output is the complement of the corresponding input. What if two of the switches are on? What would happen? So let's imagine the top two switches are on, top two tries. So E0 and E1 are high, and E2 and E3 are low. So E2, E3 are disconnected. So I have E0 and E1 on. So So what do you think will the situation at X be? Okay, so if the inputs are let's say inputs are equal. Let's say A0 and A1 are both 0. Output is 1. What if both of them are 1? Output is 0. What if, let's say, one is 0, the other is 1? Huh? Not valid. So this is like taking 5 volt or whatever, 100 volt and ground and putting them together. Not good, right? So a lot of current will flow and thing can smoke, right? Yeah. So obviously for something like this to make sense, I need to make sure only one switch is on. Otherwise, all sort of bad nasty things can happen, a lot of current can flow. But that's good for us because multiplexer, remember, we're trying to create a multiplexer. A multiplexer controlling only one control input is going to be in it. So if we are using this thing correctly, exactly one of these things are going to be enabled, and then it acts like a multiplexer or inverting multiplexer. It takes kind of input and inverts it before feeding it out. So this kind of stuff. So I have a 4:1 inverting multiplexer. Each inverter can be made using 2 transistors. So just with 8 transistors, it turns out we can make this thing. In some other courses you will learn how inverters are made and all, but trust me, this is a lot cheaper than the previous inverter that we had seen where we had AND gates and OR gates and stuff like that. So this kind of multiplexer where we basically create 4 switches and have them be connected to the output gives me a very cheap way of creating a multiplexer. If I want to create an 8:1 multiplexer, what would I do with this guy? So now I have 8 inputs, A0 through A7, and corresponding controls E0 through E7. How would I make a 8:1 multiplexer? Huh? Just what?
Add gates.
What do you mean add gates? Add more of these, just like this, and tie them together at the output again. And as long as I make sure only one of them is on, which is how the multiplexer works, I'm okay. So as long as I'm careful about operating the system as a multiplexer and never ever should have 2 or more of them simultaneously on, I'm fine. So I can make gazillion:1 multiplexer just by kind of having zillions of these things in parallel. So I can make very large fan-in multiplexers, as they call, as in like large number of inputs feeding into a single place, and create them very efficiently. So these are the tri-state multiplexers, very powerful from a circuit point of view. Yeah, so I have a bunch of, I want to skip these slides. It basically kind of shows what happens in the different settings. Okay. I could, instead of an inverting one, I could use a non-inverting, so I could use a tri-state buffer instead of a tri-state inverter, and that would be a non-inverting type multiplexer. So that works great. Okay, so now we have seen 2 ways of making multiplexer.
Why would you want to invert it?
Why would I want to invert it? Okay, so it turns out that in semiconductor technology, the basic thing, the cheapest thing you can make, cheapest gate you can make is an inverter. If you want to make a non-inverting thing, you have to put 2 inverters back to back, and therefore it costs more. Now, oftentimes it turns out that it's okay to kind of have the sense of your logic flip because it gets you the speed. So what I'll do is I'll start out with A, and then after multiplexing it becomes A bar, and then as long as I keep track of it, next stage I can again have just a single stage of inverter and kind of keep track of it. So instead of kind of making sure that every stage of my logic is non-inverting, you let each stage be inverting, and then kind of, if you need be, at the end apply correction. So this results in generally a factor of 2 faster solution. Yes. But those are details specific to CMOS technology, which is commonly used. It's certainly possible that in some other type of technology for realizing digital systems, that rule may not apply. You may actually have relays, for example, are non-inverting. Okay, if you were to actually use electromagnetic relays to create digital computers like these, they will be non-inverting. And in fact, some of the early computers were like that, or behave this way. The electromechanical machines, the old telephone exchanges. So it's a technology-dependent answer. Any other question? Okay, so we saw 2 ways of making multiplexers, but these were multiplexers where the control input was 1 hot first. Okay, so if I had n inputs, n possible sources, then I needed n control input bits. As I talked earlier, you may imagine multiplexers where the control input is binary coded. So if I have n sources, 0 through n minus 1, then my control input is log 2n bits. Okay, so if I'm making a 8:1 multiplexer, I will have 3 control planes as opposed to 8 control planes. And there was an answer from the back that one way of making this thing is that I can use my old decoder, which takes binary coded data, turns it into 1 hot coded data, and then use the multiplexers that we just saw. So that's how one could make these. So this is how we would do it. That we'll take our multiplexer, which takes 1 hot coded control input, and we are going to use a decoder, which is going to take my binary coded select. So SB stands for select, which is binary coded, is going to convert it into a select, which is 1 hot coded, and then use our regular multiplexer. So n is going to be log to m. M is going to be log to n ceiling. Okay. So remember, our multiplexers, the number of sources doesn't have to be power of 2. I can make a 5:1 multiplexer, let's say. And so if it's a 5:1 multiplexer, I will need 3 control bits on the SB side. I'll need 3 control bits out here, and then I'll use our decoder, and that decoder will be generating 8 outputs, 1 hot coded, 3 of whom I will ignore. The remaining 5 I'm going to use to control my multiplexer. So multiplexers typically do come in powers of 2 as sort of reusable digital logic gates that you will find. But in a system, eventually, number of sources doesn't have to be power of 2. It could be something else, in which case you just don't use the relevant part of unneeded part of it. Okay, so these are called binary select multiplexers, whereas the ones which we saw thus far were what the book calls, and therefore we'll call as just plain multiplexer, but you can say they are 1 hot coded selection. So 1 hot coded select multiplexers. Okay, so this just expands into it. If I'm doing a 4:1 multiplexer, then using the gate strategy, then what we do is we take, so this is kind of a bit more efficient way of doing things. One way I could have implemented is indeed shown out here, that I create a full decoder. And a decoder would have needed AND gates, and then I will have 4 outputs coming out, and I'm going to feed them out here. But you could create a more efficient binary select multiplexer this particular way. So what we do is, instead of we kind of merge the decoding functionality into the multiplexing functionality. So let's look at it this way. I have SB1 and SB0. I create inverted versions of them also. And then previously in my multiplexer, I had 2:1 AND gates. Now I have 3:1. So let's say SB0, SB1 were both 0, 0. If they were both 0, 0, we want A0 to reach B. So now what will happen is, if SB1, SB0 are both 0, 0, so let's consider this case. So look at this AND gate. This AND gate is going to see, it is getting SB0 and it is getting SB1. So it is going to see 0 and 0 here. The second AND gate, it is getting SB1, which is 0, and it is getting SB0 bar, which is 1. This AND gate, the third AND gate, it is getting SB1 bar, which is going to be 1, and it is going to get SB0 like this, which is B0. And then finally, this guy is going to get 1 and 1. As you can see out here, what is happening now is 3 of the 4 AND gates are disabled because they have a 0 at the input. And therefore, what will happen is these guys are going to output 0, whereas this guy is going to output A0. And now my OR gate has 0, 0, 0, A0, therefore it will output A0. And you can try it out for the other 4 possibilities of SB0, SB1. Exactly 1 of the 4 AND gates would be enabled, the other 3 will be disabled. So we, instead of having a separate stage of AND gates as in a separate decoder, I could kind of merge the decoder functionality into my multiplexer functionality and kind of have a cheaper realization. So while you could implement your multiplexer this way, a binary select multiplexer, it will need more gates. And by going under the hood and kind of combining them together and doing it this way, you end up with a more efficient design. So this goes to a point I was making earlier. Modularity, using these modules and writing them together, simplifies design, the process of design, but may result in a more costly design. So if you are optimizing for how much silicon area you use or what's the cost of your chip or how much power it is consuming, oftentimes you'll have to do this optimization under the hood. Now again, as I've emphasized again and again, this is not something you do manually. There are tools which take care of it for you, but nevertheless, kind of good to know what's happening. So let's try another example out here. So let's say instead of 0, 0, I had SB1 was 1, SB0 is 0. Okay. So which of the 4 AND gates would be enabled now? A2, let's see. SB1 is 1, so yeah, it would be A2. That's right. Okay, so this guy will see 1, 1. The others would see at least one of them 0, so in that case, this guy would be an A2, and rest would be 0, 0, and 0, and the output would be A2 in that case. And so on and so forth. So there's 4 possible choices. What is okay, so before we, now let's say I want to play the same game where I have binary select, I have binary coded select input, but this time around I want to use multiplexers using the tri-state buffers. So how would you do that? So let's remind ourselves. This is how it looked like. That's not a. This is how it looked like. Let's say. So here, S inputs are 1-hot coded, but I want a binary select coded multiplexer. So S, instead of S0 through S3, I'm going to give you BS0 and BS1. And now I want you to make a multiplexer. So any idea how would you do that? Any time. Could we apply one of the approaches we saw this?
Wait till just coming to F2 to the
Okay, so I could do this, right? Right. Our multiplexer is made using uh, the 5-state buffer, and I can use a separate decoder, and then that decoder is generating S0 through S3. Okay, so that's certainly be good. Question: could you do better? Could you make? Uh, could you think of some other ways of doing it by perhaps using extra tri-state inverters? So let's try to do that. It's a little bit tricky, but actually that's how digital logic first came into being. So let's try this. Let's say I were to give you this circuit. Two tri-state buffers in series, one controlled by A, the other controlled by B, and output is called Y, input is called X. So when would Y be equal to X? Huh? A is 1, B is 1, right? So you could say that Y is equal to A and B and X, right? If A is high, B is high, then I get the X. Otherwise, I get a tri-state, right? Now let's imagine I generalize this thing. I take another one. I control this by A bar, this by B, connect to the same thing, and I'm going to call this guy X0. I'm going to call this guy X1. I take yet another one. I'm going to call this controlled by A bar, control this by B bar. I'm going to call this guy X2. And then finally, I'm going to have a fourth combination, which is controlled by A and B bar. And this is, let's say, X3. One of these four combinations of two will be on, right? Because A and B can only take four possible values. So one of them will be on, and that input would be connected to them. So now I have my multiplexer, but A and B are providing the control inputs in a binary coded form now. Okay? So the other thing you are realizing is that two switches in series give me an AND-like functionality, right? For the current to flow or whatever data to flow, both have to be on. Two switches in parallel give me an OR-like functionality, right? One or the other has to be on. So that also kind of hopefully means that, I can actually do a lot more with these switches. Putting, whenever I need an AND function, put them in series. Whenever I need an OR function, I put them in parallel. And I can begin to make gates using switches. And in fact, that's how originally gates were started out. They were made using relays and basically with this kind of flow. So you can actually, just with switches and inverters, you can make arbitrary logic. And that itself can be often a very powerful mechanism of doing it. So this is the way I would create a binary select. So what we have out here is binary select 4 to 1 mux. Now the only thing which is kind of I sort of glossed over is I need A and A bar both, right? So I will need some inverters out here. I'll need both A bar and B and B bar. So I'll need a couple of inverters and then 8 of these switches. Now going back to the question earlier on, that why do we need the inverting stuff? So this is a great example where I have two stages of buffers, and I told that buffers are slower, so I might as well make them inverting, and nothing will change, right? Because I'll have two inverters in series, and that would result in positive logic in the output, and I just reduced my cost by a factor of 2 normal technologies. So this is a type of mux. So let's see if we can. So the intuition then is I can use switches like these, or tri-state buffers and all, to create mux, all sort of muxes, and the other, and actually potentially other type of logic. The other powerful thing is that you can actually you can use multiplexers to create arbitrary logic. So previously we saw we could use decoders to create any logic. A decoder was telling me which minter, right? I feed something to the decoder, and if one of its output would be high, and the output that would be high will correspond to the minter which is valid. We'll see how multiplexers can be used to create arbitrary logic. So multiplexers, you give any Boolean function and give me a large enough multiplexer, you can implement it. So let's see how that could be done. So let's say I want to create a prime number checker. So it's going to take a 3-bit number, and it is going to output 1 whenever the 3-bit number is a prime. Prime, or I guess we have always been counting 1 as a prime number, so we are going to continue counting that. So prime or 1. And this shows how we can do it. So I'm going to take my input to the function, and so if I have a n-bit input, I'm going to create a multiplexer which takes an n-bit binary select input. So since I have a 3-bit function, I need a 8:1 multiplexer. So 3 bits can specify 8 possible inputs. So I'll use an 8:1 multiplexer, and I'll tie the input to whatever value I need for the corresponding thing. So in this particular case, this is 0, 1, 2, 3, 4, 5, 6, 7. So when input is all 0, source number 0 will be selected, and what I'll do is I'll tie source number 0 to 0, to electrically ground it. And therefore, whenever input is 0, 0, 0, the output will be connected to 0, and that's what we want. Let's say SB represented 5, 1, 0, 1. So then source number 5 will be selected, and since output we want is 1, so we'll make sure that the input for source 5 is connected to 1, which would mean a high voltage. So we connect it to high voltage, and therefore output will pick that up. So literally what we are doing is we are taking the output column of a truth table and mapping them to the inputs out here. So if my truth table has 16 entries, then I will have a 16:1 multiplexer. So I need that many things. And so if you give me a n-bit function, then I need a 2 to the power n:1 multiplexer. And then I'll just take the entries of my truth table and kind of map them out here, essentially tie them to logic 0 or logic 1, depending upon what the truth table says. You could go better. Imagine if I had little memory cells sitting out here, something I can write into in software, and I had this multiplexer. You give me a function, I'll write the appropriate entries into the memory cells, and I'll implement that logic function in hardware. So I can create programmable hardware if I have these large multiplexers and little memory cells. Or maybe alternatively, at each one of these input, I may have electrical switches, sort of a fuse kind of thing. So my chip, when it comes in, let's say a chip comes in, it has a multiplexer, and it has 2 fuses. One fuse is connected to 1, the other fuse is connected to 0. And now the designer tells me that this input to the multiplexer needs to be tied to 1 because that's the function we are implementing. What we'll do is we'll take some high current or laser or whatever and zap this fuse. We'll blow this fuse. It will melt away, and then the input will just be connected to 1. So you can make these kind of programmable hardware where you buy the chip, they're capable of implementing any function of up to some n bits, and then you design your stuff in software. The software tells some sort of a programmer hardware to go and zap some of these fuses, and now your chip is programmed for your function. So that's a very powerful thing, because now instead of every time you have a new design going to a factory to get chip made, now you can buy these chips which are ready to be written to make your device. And even better, if instead of fuses you had memory to which you can just write like you write the in software. You just kind of send some bits to your chip, and the chip totally changes its personality. So these kind of things, they go under the name of programmable logic devices, I mentioned earlier, or field programmable gate arrays and all, but they all rely on this concept that multiplexers and decoders can be used to implement arbitrary logic, and therefore they're very powerful. It comes at a cost. It's inefficient to do it this way, but oftentimes, again, sort of the cost of making something custom and the time it takes is overridden by I can get stuff out to the market rapidly, I can fix bugs easily, all those kind of side benefits come. So in recent 10, 15 years, these kind of devices have become extremely popular and kind of are very, very commonly used because their merits kind of, particularly in terms of time to market, they just override their other disadvantages. So, moral of the story out here, Mux, just like decoders, I could use them to implement any function subject to how so many bits I had out here. So with a 64:1 multiplexer, I can implement any logic function of how many inputs? So if I give you a 64:1 multiplexer, what I can implement any function of how many inputs? 6, right? And so on and so forth. So, so that's kind of the power of Muxes. Could we reduce the size of multiplexers? So thus far we talked about, okay, so I have when I'm implementing logic using multiplexer, I'm limiting myself to time the input to 0 or 1. So we saw that out here, that in this case, all the inputs were tied to 0 or 1 only. So they were either grounded or they were connected to a logic 1 voltage. Could we do better? So let's take this example again. So what we do is the following. I think I'm using the same example. Let me make sure. Yeah. So let's look at this one. I've written my truth table in a slightly different fashion. So what I do is I have SB1 and 0 I put in this column. It's the same example, the prime number example. SB2 I put in a separate column. And what I'm going to do is I'm going to use a 4:1 multiplexer. I'm going to feed SB1 and SB0 to the control input of that multiplexer. But the data input of the multiplexer, I'm going to tie them to either SB2 or SB2 prime, SB2 complement. So now let's look at this way. So I have SB1, SB0 is 0, 0. If SB2 was 0, then my input would have been 0, 0, 0. So my output should have been 0, right? It's not a prime. If SB2 was 1, then I have 1, 1, 0. Sorry, I have 1, 0, 0, which is 4, which is also not a prime. So in that case, my output is unconditionally 0. Okay, that is for both the cases, whether SB2 is 0 or SB2 is 1, my output are 0 in both cases, and therefore equation is 0. Let's take the case where SB10 are 0, 1 and SB2 is 0. So I have then 0, 0, 1. That is 1, which by the book's weird logic is a prime, so therefore output is high. And if SB2 is 1, then my input is 1, 0, 1, which is 5, which is also a prime. So in this case, again my equation becomes 1. Let's take the next one. In this case, if SB2 is 0, so my input becomes 0, 1, 0. which is 2, which is prime. So we put a prime out here. And if SB2 is 1, then I have 1, 1, 0, which is 6, which is not a prime. So now I have 1, 0. SB2 was 0, 1. It's the invert of that. So I say equation, the input, I will tie it to not of SB2. So the input number 3 of my mux, I'm going to tie to not SB2. And then finally, if SB10 is 1, 1, if SB2 is 0, my input is 0, 1, 1, which is 3, so which is a prime. And if SB2 is 1, input would be 1, 1, 1, which is 7, which is also prime. And therefore, I get this. So now my one prime function, one or prime function can be implemented like this. I have a mux, which is a 4:1 mux. I tie it to 0, 1. I tie this input to not of SB2, and this one to 1. And by the previous logic, I get its prime. This, as compared to this, here I have a 8:1 mux. So and now I have a 4:1 mux. So I need roughly half the transistors in my mux with the addition of an inverter out here, which actually even in the previous one you would have needed. So I actually have a significant reduction in the size. So if I'm willing to feed something other than 0 and 1 to the input of my mux, I can create much more efficient logics this particular way. So, so generally what happens in these programmable chips is that they give you a supply of mux, and the inputs to those mux, not only can you say it's 0 or 1, you can actually also connect them to some other signals. And then pretty soon it becomes very hairy for humans to deal with it, but design tools are very good at doing that kind of mapping. So they can map very complicated logics to these kind of things. You can, if you give a mux and a flexible enough wiring around it, you can create very, very complicated logic. Is this what I did not clear to anyone? Just speak up. Or no? How did I get not SB2? Okay, so look at this row again. Okay, so in this row, SB1, 0 or 1, 0. Okay, so that means I'm selecting the input corresponding to 1, 0, which in our parlance is going to be input label 2, okay, source number 2. If SB2 was 0, then the input to my function is 0, 1, 0, which is the number 2. So that's prime, therefore this is 1. And if my SB2 was high, then the input to my function is 1, 1, 0, which is 6. And that is not a prime, so this is a 0. So this you agree, right? So this would be 1, this is 0. Now look at this. When this is 1 when SB2 is 0. And this is 0 when SB2 is 1. So I can capture this thing by saying it is opposite of its complement of SB2. Right? Okay, so that's what we have out here. The other 3 rows were simple because they were independent of SB2. They were both the columns were the same out here. So you have, if it is 0, 0, then the output equation is unconditionally 0. If it is 1, 1, you tie it to 1. If it is 1, 0, then that means it's complement of SB2. And there's another possibility which didn't occur here. It could have been 0, 1. If it was 0, 1, then I would have said equation is SB2. Okay, so so I take my inputs to the function, feed some of them to the control input of the mux, and the others I feed through gates or inverters or whatnot to the inputs of the multiplexer. Okay, that's kind of the idea. So there's a trade-off. I can always use a large multiplexer. So if I have n inputs to my function, I can use 2 to the power n:1 mux, or I can say I'm going to use a smaller mux and then use some additional gates, and you play with it until you come up with kind of a small enough implementation. And again, like I said, so software tools excel in being able to do it. Small examples you can see how it works. building muxes out of small muxes. So we are fond of doing bigger things from smaller things. So we did it for encoder, decoder. Let's do it for multiplexers. So we give you a supply of small mux. Let's say a supply of 2:1 mux or 4:1 mux, and I want to create a bigger mux, 16:1, 32:1. So how do I gang them together? How do I? That's kind of the story out here. So suppose you have one multiplexer with n inputs and another multiplexer of m inputs. So I give you two muxes, one which can take n:1, n sources, feeds them into 1. Another one has m sources, feeds them into 1. And what we can do is we can now create a new multiplexer, as I'll show, which takes m times n input and does that. So let's say, and with this logic, you can easily show that if you have a if you have an infinite supply of 2 input multiplexers, you can create an arbitrarily large multiplexer out of that. Okay, so let's see how that would work. So what we have out here is I have 4:1 muxes. So I have a supply of mux which take 4 sources and multiplex them into 1. So what I've done out here is in stage 1, I have 16 sources. I feed 4 of them into this mux, another 4 of them to this mux, another 4 to this mux, another 4 to this mux. And then I take their outputs. I have 4 of them, and I feed them into a second stage mux, and then feed this out. So now let's say I want to select A4. So A4 I can think of as, I'm basically saying that I divide my sources into groups of 4, and I can say the top one is group 0. This is group 1. This is group 2. This is group 3. And the group number is decided by upper 2 bits. Remember, since I'm doing 16:1, I would have had 4-bit control input. So the upper 2 bits of that will tell me which group I am in, and the lower 2 bits are going to tell me within a group which bit number I want, which source number I want. So if it was A4, A4 would be expressed as 0, 1, 0, 0. This is the group number, and this is saying which source within that group. So I'm going to feed this 0, 1 to this mux, and I'm going to feed this one to each one of the 4 muxes. So it is going to feed out here. So what will happen in our example is it's 0, 1, 0, 0. So lower bits are 0, 0. So they are feeding to each one of these 4 first stage mux. So here, what will I see? Output of mux, top mux. What would that be? Which A? A0, right? Because it's going to select source number 0 of this mux, because I'm feeding 0, 0 to each one of these. What would it be here? A4. This one would be A8, and this one would be A12. The upper 2 bits I'm feeding out here is basically saying which group number I select. And since this 0, 1, so I'm going to select group number 1, which is this guy. So we'll see A4 coming out here. And you can check the same concept works everywhere else. So the second stage mux, the one at the output, is telling me which group. And the first stage mux is saying within group which source. And you can imagine, I can play this game at multiple levels. I can have groups, subgroups, and then within the subgroup, or multiple levels of these. So if I were to make, let's say, a 32:1 multiplexer using 4:1 mux, what I could do is I can have 8 first stage mux, then a second stage with 2 mux, because I have now 8 of those, and then a final mux, which is another 2:1 mux, or I can use a 4:1 mux and ignore 2 of its inputs. So I can, in 3 stages, I can make a 32:1 mux. And so smaller muxes can be ganged up together to make bigger muxes. Of course, if I were to simply make one large mux, I will have fewer stages. But whereas by using this, I'm introducing more stages of mux. I have a slower design, but I have a smaller design and I have more flexibility. I can kind of create complicated designs easily, which may not be available otherwise. So small muxes can be ganged up to create big muxes, much like small muxes, small decoders could be ganged up to create big decoders, and small encoders could be ganged up to create big encoders. Any questions on this one? That how muxes are being ganged up? Okay, so next module that we'll explore is a very useful one. It's used quite a bit, and it's called arbiter. So what does arbiter in normal English do? What is an arbiter? You hear about often, like if you ever care to read the contracts that companies and all make you sign, they say you cannot sue them. It has to be done through legal arbitration. So what is an arbiter?
Person that is involved with either party.
A person that?
Is involved with either party.
That is true, but what does an arbiter do? What is its role? Yeah, it's like an umpire, referee, whatever. Yeah, it's competing parties. It selects a winner, right? Or selects this person is the right one. So arbiter, multiple people approach, and it selects one. We often face these kind of situations in digital systems, computers, that there may be multiple things seeking attention, and the computer has to give attention to just one of them. Other places, like many games, like Jeopardy. So I'm sure some of you watch it. Like when the players are seeking to answer the question, they press a button, and the one who hit the button the first gets the chance, right? So there is some circuit sitting there which is monitoring the button outputs and selecting which one is the first one, right? So likewise, for example, when multiple radios on our Wi-Fi network, when they seek to transmit a packet, if they were to all transmit together, they will collide. So there is some mechanism out there, some arbitration mechanism, which selects, okay, it's your turn to transmit. Okay, so in a lot of these places, you have this functionality sitting there which selects a winner. So that's what an arbiter does. So arbiter takes requests from multiple devices which are interested in using a resource, and then selects which one of them gets access to the resource. Okay, and it has to do it very carefully, because what may happen is there will be multiple parties coming in exactly simultaneously, right? I mean, that's kind of your worst case situation. So you cannot simply say whoever came first gets it, because you may have people coming in exactly simultaneously. So what happens then? So let's say there are multiple parties come in who want to kind of use the source exactly at the same time. Again, take real life analogy. What would you do? Let's say you are parceling something out to kids, and 2 kids come to you at the same time. How do you break the tie? Huh? Choose at random. What strategy?
Rock, paper, scissors.
Huh? What did it say?
Rock, paper, scissors.
Okay, whatever. You will have some criteria, right? Okay, someone looks more beautiful. You may have gender bias, you may have race bias, you may have whatever, right? Some criterion that you will pick. Or it could be as simple as, I don't know, professors get more priority than students, right? Or something. So it could be some built-in hierarchy in the system. So arbiter will also need some sort of a rule saying how to break the ties, right? So arbiter selects a winner. based upon some criterion. Okay, so now what we want is the following. Let's imagine there is memory. There are many processors which want to read or write to that memory. And normally, let's say, read and write happen rarely enough, so there's no competition. A processor wants to access it and gets it. But it may happen that more than one processor want to access the memory at the same time. So they all say, I request access to the memory. And the arbiter has to now decide which processor should go ahead and get access to the memory, because if you let both of them go through, there will be some data corruption. So the arbiter logic looks like the following. It has an n bit of request, R stands for request, and it has n bits of grant, G stands for grant. So what happens is in any given decision cycle, arbiter will see all the different parties are going to present their request. Some of them may say 0, which means they don't need the resource. Some of them may say 1, they need the resource. Arbiter's job is to output, to give control to one of them. Okay, if at least one party asked, then it will give to one of them and not to the others. And the idea is the following, that we in this particular arbiter, we are going to give the priority according to their location within this vector R. So if you think of R as an n-bit vector, then what we'll do is we'll say Gi is 1, that is I give the ith party access to the resource if two conditions are met. Ri is 1, that is that party requested the resource, and secondly, Ri is 0 for everything, every j less than I. Okay, so in this particular case, if for example 0th party requested, then R0 would have been high, and then the resource would go to that. So the priority is that looking from the 0th bit, I am giving the priority. 0th bit has the highest priority, then the first bit, then the second bit, and eventually the n-1th bit. So that's the logic out here, that a party has to request a resource, and no party with a lower index should have requested the resource. That's the functionality that we want. So we seek to implement this. So let's see how we are going to do this. So one way of doing this thing is, I have n bits. I can consider all possible combinations of n. There are 2 to the power n of them, and then decide who is the winner. Okay, so I'll have a gigantic truth table. These arbitration logics sometimes have to deal with a large number of requesters, so that can get very complicated. So it would be nice that I can create a logic which can A, scale to large number, and B, should be something that I can easily change. I can add an additional requester without having to redo kind of the whole logic. So again, one way is our traditional approach. You construct the truth table and kind of do it. The other is that we think of something better to do it, which is more scalable. So let's look at that. So what we so the first approach, where you just do it using truth table, Carnot maps, whatever. We have been doing many different designs. You can do this one also the same way. But let's look at the scalable way. So the idea out here, and this is a pattern we'll see again and again, we'll first create a 1-bit arbiter. And then we'll gang up 1-bit arbiters to create n-bit arbiters. So the idea, the way it works is the following. I'm going to look at what is happening at the ith bit. At the ith bit, I'm getting the request from ith requester, and I'm going to generate the output for that requester, the grant signal for the ith requester. And my logic is the following, that if ith requester requested and no other lower I has requested, so that is, I am not already granted to something which has a lower I, then I should grant. So that's the logic that you are seeing out here. I'm saying grant I is equal to Ri, that is, ith has requested, and there is a signal, no one yet. So it's basically saying, among the lower I-1 bits, no one yet has requested. Okay, so this is a signal that the bit number I minus 1, arbiter for bit number I minus 1 will send to me. So the previous stage is telling me whether it has someone has already taken someone higher priority, that is lower bit position, has already requested the resource. So this is saying no one yet. If that means this will be high when none of the previous bits have requested. So 1 if no bit less than I requested, right? So Ri for R0 through Ri minus 1 was OR0. In that case, this guy would be 1. And if that's the case, then I should give resource I the grant, because Ri is 1 and this is 1, then I will get this guy 1, right? So if it is, if this is 1 and this is 1, then grant I would be 1. And if either one of these conditions are not met, that is if I did not request it or something previously requested it, then in that case the grant here would be 0. So that's the grant I'm generating. But then I also have to generate the signal for the next stage. So the logic for the next stage would be that if anyone previously requested, if this guy was 1, then of course the output has to be 1 because something previously requested. Moreover, if this guy requested, if Ri was 1, then also the output should, if Ri was, this one should be 1, that is no one has requested yet, if no one and 0 through I minus 1 requested, and this guy also did not request, right? So if Ri was 0 and no one yet was 1, then this output would be 1. If no one yet was 0 from the previous stage, then this one will also be 0. And likewise, if Ri was high, then also this guy will be 0. So we are basically saying previous stage tells me whether it has seen a request thus far, and I'm going to tell the next stage whether any of the previous stage or I or my stage has seen a request. And that's the role. So this is basically, this logic is kind of doing that. It's basically saying, so this one is 1 if no request in 0 through I minus 1 and no request I. So that's what this arbiter is going to do. It's basically taking a signal from the previous stage, which is telling whatever has happened thus far, and then it's going to generate a signal for the next stage, and it's going to also generate the output for this stage. And now, as you can imagine, I can gang them together, right? Because each stage, the logic makes sense. I can gang them together. What do you think should be the input? No one yet for the 0th stage. So I have to kind of worry about what happens when I is 0, very first stage. But still it has this input, no one yet. What would you tie that to? 1, right? Because there was no previous bit, so no one yet requested. So stage 0, I would tie this input to high, and then kind of literally just gang these things together. And then you want to add one more arbiter, you just add it to this chain. So the logic looks like the following. Okay, this thing that you are seeing out here, this is logic 1. It's tying it to some high voltage. Okay, so that's how. So you want to add up. In this case, I already had 4 requests, and you want to add a 5th one. You just add one more state. So it gives us a scalable design. I can gracefully scale it to more and more bits. But it comes at a cost. You see some problem with this design?
Do I have to really use the function to aggregate since
Yeah, you can optimize it. Yeah, what you're saying is since it's 1, I can kind of simplify it. It's just that if you just want to have a single type of thing, then you just decide to 1, but you can always optimize. So the point he is making is, since this guy is 1, I really don't need this AND gate, and also this guy gets simplified. And valid point, you could do it, but sometimes you are just given a black box and you're trying to create something. Okay, so as I'm adding more stages, what is going to happen to the number of stages my signal has to go through? Delay. It's blowing up, right? It's increasing proportional to n. If I have n inputs, n requesters, I will have n of these stages. I have this long path, right? My delay is going to keep increasing. This is a delay. These are often called critical paths. That is, they decide how slow my circuit is. So what's happening is the critical path, in this particular case, the delay is proportional to n. So it's increasing linearly, which is bad, right? I mean, you would rather like to increase it more slowly than n, perhaps like logarithmically or some slower function. N means it's increasing proportionately, which is just, it's not, I mean, you could be worse, it could be n squared or something, but that even n you would like to avoid if possible. So it's a simple modular approach, but it does result in a slower circuit. So I could do things differently. So in this case, so again, this is the approach that I just described, where I look at one stage at a time. But I could also do is that handle all the stages together. So for example, if I look at G2, then G2 basically says R0 should be 0, and R1 should be 0, and R2 should be high. So I put that logic out here. G3 says that G3 is high when R0 is low, and R1 is low, and R2 is low, and R3 is high. And so forth, I could do that. In this case, the delay from input to output is a single gate, but I have a costlier structure. My gates are increasing in number of inputs, so I have costlier and costlier gates. But this is the kind of circuit you can imagine doing. Like imagine if I was creating a 64 input arbiter, then by the time I reach stage number 63, I would have a 64 input AND gate sitting out there, immensely costly. Whereas in this one, each one of my gates would remain smaller. So this approach, using one-bit entity and ganging them together, is often leads to a more efficient design, but it could be a slower design because I have a long delay. Whereas this right approach could lead to a faster design, but it might be more area hungry and more power hungry. And again, this is exactly what kind of trade-offs that people who design these systems have to kind of deal with. Sometimes speed is paramount, sometimes area is paramount, and decide what is important. So which one is better? The answer is depends. Okay. So we talked about it, delay. Okay.
Why the look-ahead approach faster? I mean, if we have more inputs to the end case, then the end case itself will have a lot.
Excellent point. The AND gate itself would have a larger delay, but typically the delay through that larger AND gate would still be faster than going through 64. But you're right. I mean, it's not obvious from what I've said that why would it necessarily be the case. Unfortunately, only your circuit courses will get into that. I can always make gates faster by making fatter and fatter transistors, huge transistors. So, sort of circuit gains. Any other questions?
What if 0, 0 happens? It means that if you don't request it and something
Which one? What are you?
When bit was requested and you don't request it, if instead you receive 0 in, as in no bit was requested yet, and you don't request it, it still comes out as G is 1. That's it.
No, is there a specific text you're referring to on my slide, or
No.
or just here? Okay.
Or do we just assume that it's always 1?
Well, so it's possible that all the G's are going to be 0, but no more than one should be 1, right? Okay. And so the question is, what happens if
The constant is 0, or should we just assume it's always 1?
which constant are you referencing?
It's here.
Oh, that one. This guy?
Yeah.
Okay, so this is tied to 1. Okay, so, and the point made by student here, which is, since tied to 1, I can simplify, this thing actually becomes just a pass-through, and this becomes inverter, so I can simplify logic a little bit, but that's a detail. Any other question? Okay, so let's see, time-wise, we have a few minutes remaining. I would, yeah, I think I cover this one. So, priority encoder. This is one more module. So, what priority encoders do is the following. They take an n-bit input signal A, they produce an m-bit signal output, and it indicates the position of the first 1 bit in A. So the idea is the following. My input is a vector. And what I'll do is, so my input is n bit. So let's say n was 8. So input is a vector. Let's say my vector is 0, 0, 1, 1, 0, 1, 0, 0. Okay? Do I have it right? Yeah, 8. And I'm counting from bit 0 through 7. My output is going to indicate which is the first high bit. So I'm going to start from this side. I'm going to scan until, and I'm going to pass through all the zeros, and I'm going to hit a 1 eventually if I do, and I'm going to use that. So I see in this particular case that there is a 1 at position number 2. So I'm going to output a 2 on the output. Since my positions go up to 7, so in this particular case, m is going to be 3. So I'm going to output 0, 1, 0 in this example. So what's happening is we are basically saying who's the winner, who is the highest priority requester currently. So, and high priority goes to lower bits. So I'm going to scan from the lower bits, and the first entity I find who's requesting, I'm going to say that's the winner. It's possible that there is no winner, in which case nothing happens. But if we know that there is always going to be at least one requester, then I would be able to give a position for that. So that's what a priority encoder is doing. It's basically saying, it's encoding the priority, it's saying who is the highest priority entity out here. So the way you can implement this thing is to use an arbiter followed by an encoder. So our arbiter was giving me essentially one of the G's would be high, indicating who was the winner, and that effectively is a one hot coded thing. And then all I'm doing is I'm doing an encoder, which is taking that one hot coded stuff and putting it into the binary. So in the example I have, where we have 0, 0, 1, 1, 0, 1, 0, 0. So 0, 0, 1, 1. And what did I have? 0, 1, 0, 0. And the way we had designed the arbiter, we were starting from the low bit. So which G would be high? What would the arbiter produce? So arbiter is getting 3 requests. Request from number 2, number 4, and number 5. So of the 8 G0 through G7, which of the Gs would be high? So you are going to start from the 0th bit, right? 0 didn't request it, 1 didn't request it, but 2 requested it. So G2 would be high, and then subsequent stages would again be low. So in this particular case, you would see that G would look like 0, 0, 0, 0, 0, 1, 0, 0. That's what G would look like, right? That it's basically declaring the winner to be this guy. And this input is now one hot coded, so our encoder is now going to produce 0, 1, 0 because position number 2 is high. So I can create a priority encoder by ganging an arbiter with our encoder. One. So priority encoder basically says which position won, which was the highest priority requested, what's the ID of that. That's what it is giving out there. So let's stop out here.